Hi everyone, this is part 2 of our look at the technique of integration using partial fraction decomposition. So if you haven't seen part 1 yet, go back and watch that because I'm going to spend less time today explaining when and how you do partial fraction decomposition and more time just looking at a few extra cases. So in part 1, all of the rational functions that we looked at had denominators which factored into products of terms, none of which were repeated. So in today's lesson, we will see some examples where there might be a factor in the denominator which is raised to a power which is not 1. So we might have a factor squared or cubed or something like that. We will also take a look at what to do if your starting rational function has the property that the power of the numerator is at least as large as the power of the denominator. You first have to make an adjustment to your rational function so that you match this property. Okay, let's go ahead and get going with an example of this. Let's start with this example. We are looking at 2x squared plus 15x minus 18 over x squared plus 6x minus 7. So in this case, we have a ratio of quadratic polynomials. The degree of the numerator is the same as the degree of the denominator. We want to fix that first, then we'll do the partial fraction decomposition, then we'll integrate. So we will do several things with this example. Okay, so here are two ways to take this rational function and rewrite it so that the degree of the numerator in any rational expression that we're looking at is less than the degree of the denominator. The first way is kind of your go-to default way of doing this sort of problem, and that's to use long division. Literally, we have a division here, so it's a quotient. Let's take the numerator, 2x squared plus 15x minus 18, and literally try to divide that by the denominator. So x squared plus 6x minus 7. Okay, this is long division just like you learned in school, except if you haven't done it before with polynomials, I'll show you what to do. This isn't going to divide perfectly because if it did, we wouldn't be looking at this to begin with. So this isn't going to be a perfect division. Instead, we're going to divide it as much as we can, and then we'll have a remainder at the end. So here's what we'll do for this example. We'll say, how many times does x squared go into 2x squared? I just write that here. Goes in twice. So x squared times 2 is 2x squared. Now let's take this 2 and multiply it by this polynomial on the left. I'll write that here. So 2 times x squared is 2x squared plus 12x minus 14. Then just like in regular long division, we'll subtract this from this. Okay, so the 2x squareds are going to cancel out. We will have 15x minus 12x, so that's 3x. And then negative 18 minus negative 14, which is minus 4. Okay, take a look at that. For this first example of long division, let me interpret what this is saying. So what does the 2 and the 3x minus 4, where can we visualize them in relation to the starting rational function that we had? Well, we tried to divide 2x squared plus 15x minus 18 by the original denominator. We said it went in twice and left this as a remainder. So in other words, we could say 2x squared plus 15x minus 18 equals twice x squared plus 6x minus 7, with this as a remainder, so plus 3x minus 4. Now what I could do is take this equation and divide it by x squared plus 6x minus 7. That would leave me with, let me go ahead and do that. So I'm going to divide by x squared plus 6x minus 7. These cancel. This is our original quotient. So we're now saying that our original rational function equals 2, that's this part here, 2 plus the remainder divided by x squared plus 6x minus 7. This has the nice property that the power of the numerator is less than the power of the denominator. So we're actually done at this point. When you get to a moment where any x term you have left, your highest power down here in the remainder, is less than this highest power here, then you're done. Okay, so let me rewrite this as, I'm going to switch markers as well. So our rational function, I'll just write RF, is now 2 plus 3x minus 4 divided by x squared plus 6x minus 7. If we want to integrate what we started with, we can integrate this instead. And now this is ready, particularly this part, for the partial fraction decomposition. Long division, like we just did, would be the classic way to take this rational function and write it so that it's ready to go for partial fraction decomposition. Let me show you an alternative that I like, and if you like it too, that's great. But if you don't see how to do this, that's okay. Just stick with long division. So what I'm going to do is take terms in my numerator and add and subtract anything I need in order to get something in the numerator that will cancel with the denominator. Let me just go ahead and do it. So I'm going to take 2x squared, that's what we started with, the first term in our numerator, and I'm going to add to that 12x because this is twice the quadratic term in the denominator. So let me make this twice the linear term in the denominator. And then I would also like to have twice the constant term from the denominator. So how about minus 14? Okay, so everything I've got so far is part of the numerator I'm in the process of writing down, but it looks like twice the denominator. So 2 times x squared plus 6x minus 7. Now I just need to make sure I'm not actually changing my numerator. So let me balance this so that it works out back to 2x squared plus 15x minus 18. So I need to add to this 3x and subtract from it rather 4. Okay, so now if you look at this, overall it's 2x squared plus 15x minus 18, which is the numerator that we started with, but I've reorganized that numerator so that this actually looks like the denominator, just times 2. Okay, if we take this and divide it by the original denominator, x squared plus 6x minus 7, then what I can do is now break this into 2 fractions. So this will go into the first one, this will go into the second one. And maybe you see what we're doing. We're actually just going to get back what I've already written down, which shouldn't be too surprising. If I take this and set it over the denominator, I can even factor out the 2 to write 2 times x squared plus 6x minus 7 all over x squared plus 6x minus 7. And then plus the rest of it. So plus 3x minus 4 over, trying to make this horizontal line visible, over x squared plus 6x minus 7. Then after doing that, because of the way that we made this essentially a duplicate of the denominator just times 2, we get cancellation. And this returns us back the form that we just wrote down. So 2 plus 3x minus 4 over the original quadratic denominator, and now we're ready to go for partial fractions. Now that we've rewritten our rational function, we're ready to do partial fraction decomposition on this part. So you can ignore the leading 2 for a minute. We just need to take this and break it into smaller pieces so that we can anti-differentiate. So this is exactly the type of example I did in the first video, which means I'll work through this, but a little bit faster and with less explanation this time around. So what we have is 3x minus 4 all over the denominator, which factors into, let's see, x plus 7 times x minus 1. Okay, this can be broken apart into 2 rational functions of the form a over x plus 7 plus b over x minus 1. Now let's multiply both sides of this equality by the common denominator of x plus 7, x minus 1. On the left, we get 3x minus 4. On the right, we get ax minus a plus bx plus 7b. Now let's match like terms. That gives us 2 equations for the 2 unknowns a and b. So in particular, 3 is a plus b, so that 3x is ax plus bx. So 3 equals a plus b. And then negative 4 is negative a plus 7b. Okay, so that's 2 equations for 2 unknowns. If we add them together, the a's will cancel out right away. So if I add these 2 equations, on the left we have negative 1. A's cancel, and we're left with 8b on the right. That tells us that b is negative 1 over 8. Now that we know that, let's use the first equation to solve for a. A is 3 minus b. So that's like 24 over 8 minus negative 1 over 8. So the other constant a is 25 over 8. Okay, so in our partial fraction decomposition, our new expressions are going to be 25 over 8 over x plus 7 and negative 1 over 8 over x minus 1. Thanks to all the work we've done, if we wanted to do the indefinite integral of the rational function that we started with, we can now just anti-differentiate term by term the quantities 2 plus 25 over 8 over x plus 7 plus negative 1/8 over x minus 1. Each of these is ready to go. So we have that the antiderivative of the first one is 2x. The antiderivative of the second one is just that leading constant, 25 over 8, times natural log of the absolute value of x plus 7, and then minus 1 over 8 times natural log of the absolute value of x minus 1 plus a constant of integration. So our starting rational function, once we did all the work breaking it into two pieces so that the numerator had degree less than the denominator and then doing the partial fraction decomposition, it turned into a very simple integral. Okay, now let's do the partial fraction decomposition for this rational function, 2x squared plus x minus 8 all over x cubed minus 4x squared plus 5x minus 2. Now we have a cubic denominator, which can be difficult to work with in terms of if you just start trying to factor it right away. But here's something to keep in mind whenever you're trying to factor a denominator, and if you're working with partial fractions, you probably can factor it. Here's what you should try. Look at the constant for your denominator. What are its factors? Well, plus or minus 1, plus or minus 2. You want to see if any of those are roots of this cubic polynomial in the denominator. This is from something called the rational root theorem, which is something that you may have learned in an algebra class, but it says that basically if you have a leading coefficient of 1 for your polynomial, which is what we have here, then a rational root, meaning a nice root, for this cubic polynomial should divide into negative 2. Okay, so let's just try 1. What happens if x equals 1? Let's plug 1 into the polynomial in the denominator. We would have 1 cubed minus 4 times 1 squared plus 5 times 1 minus 2. So that's 1 minus 4 plus 5 minus 2. That is actually 0. So that tells us that x equals 1 is a root, or in other words, x minus 1 is a factor. So we found one of our terms. We just need to now take this cubic polynomial, divide it by x minus 1 to get a remaining quadratic, and then see if we can factor that in the usual way. You could use synthetic division here. If you've seen synthetic division, you might like it for doing this kind of division better. I secretly do as well, but I'm going to use long division because long division is one of our techniques of this lecture. So to do the long division here, I'm going to divide the cubic. So x cubed minus 4x squared plus 5x minus 2. I'm going to divide this by what we already know is a factor, x minus 1. So if I do the long division correctly, there should not be any remainder at the end. This should divide perfectly. Okay, so how does x go into x cubed? It needs to be multiplied by x squared. That leaves us with x squared times x and x squared times negative 1. Like that. Now when I do the subtraction, the first terms cancel out, and I'm left with negative 3x squared. When I'm long dividing polynomials like this, I just bring everything down. So I just keep bringing all of the remaining terms down. I need to divide negative 3x squared by x. So that should be negative 3. negative 3x. There we go. So negative 3x times x is negative 3x squared, and then plus 3x. We'll subtract that from what we wrote just above. The leading quadratics cancel. Then we have 5x minus 3x is 2x, and then the negative 2 comes down, the negative 2 minus 0. Now, x needs to divide into 2x. That happens if we multiply it by 2. And now you see the perfect division. So 2 times x minus 1 is 2x minus 2. And so we have a remainder of 0. Okay, so what this tells us is that this cubic factors as x minus 1 times x squared minus 3x plus 2. We're not done yet because we can actually factor this quadratic. So this is going to be x minus 1 times x minus 2x minus 1. Now, notice I have 2 copies of x minus 1. So I can actually write the denominator now as x minus 1 squared times x minus 2. Now that we know that the denominator can be factored as x minus 1 squared times x minus 2, I'll give you a moment to finish copying this down, and then I'm going to erase everything, and we will do the partial fraction decomposition for this rational function, given that this is the factored form of the denominator. Notice we'll have to talk about what to do with a repeated term. Okay, now let's do the partial fraction decomposition for this example of having a repeated factor in the denominator. This is a repeated degree 1 term, but the general principle, which we will see again in the future in this video, is going to be for any type of polynomial you have here, which is irreducible and raised to a power higher than 1. So what we'll do is first treat x minus 2 in the usual way. So that's just degree 1. It will have a constant unknown numerator. Now, the thing about x minus 1 is what kind of fraction combinations might yield this as a common denominator? Well, certainly if I had something over x minus 2 plus something over x minus 1 squared, you just partner up their denominators and you get this. But there's another type of expression that we could add to that sum, which would also have this as a common denominator, and that would be a term that only had one copy of x minus 1. So what we want to do is write this twice. We'll say b over x minus 1 plus, and let me write it and then I'll explain it, c over x minus 1 squared. So this is the most general form of a sum of rational functions with these denominators, which would have this as a common denominator. So the common denominator for these 3 expressions is literally x minus 2, and then well, this would be one copy of x minus 1, this is another x minus 1 term, it would be this. So that's one thing to remark upon in this partial fraction decomposition, is that when you have a repeated term, so a factor raised to a power, you need to have multiple copies of terms that correspond to that particular factor in the denominator. So here we have 2 expressions that correspond to x minus 1 squared. The other remark I'll make is if you look at this, you might wonder if I've done this correctly, because this denominator is quadratic. And in the past, we've said that when you're expanding an unknown partial fraction decomposition and you have, say, a degree 2 denominator, then your numerator should look like cx plus d. But what you find for repeated terms is that it's always going to be the same style as this numerator. If you had an extra, if I put cx plus d here, this would be 0. That would always happen with repeated terms. So you can test it on this example if you like, but you'll end up seeing that that leading term would have to be 0. So what you do is you take your basic term here and duplicate its style, so just a constant in this case. Okay. Now that we've got our decomposition, the rest of it is the same. We just imagine cross multiplying or multiplying both sides of this equation by that common denominator. That's going to leave us on the left with 2x squared plus x minus 8. And on the right, we need to multiply a by x minus 1 squared. We only need to multiply b by x minus 1 once, and then also by x minus 2. And then c only needs to be multiplied by x minus 2, like that. Let me pause here and let you get to 3 equations for 3 unknowns, and then we'll finish the problem together. Okay, let's go through the algebra now. I will expand everything on the left. So this is going to be ax squared minus 2x times a, so minus 2ax plus 1 times a plus bx squared minus 2x minus x is minus 3x, so minus 3bx plus 2 times b, so plus 2b plus cx minus 2. Now we can match coefficients. Let's do the constants first. On the left, we have negative 8. And on the right, we have a plus 2b, minus 2c. There we go. Minus 2c. Then we have degree 1. On the left, we have 1x. And then on the right, we have negative 2a. Then minus 3b plus c. Then for degree 2, we have 2 equals a plus b, and that's it. Okay, I'm going to do substitution because this line tells me that a is 2 minus b. So now I can rewrite the first 2 equations where I will take a every time I see it and replace it with 2 minus b. Okay, so we will have negative 8 equals, instead of a, I'll write 2 minus b, and then plus 2b minus 2c. And then for the second equation, we have 1 equals negative 2a, so that's going to be minus 4 plus 2b, and then minus 3b plus c. Okay, let me just check that I wrote that correctly. Minus 2 times 2 is negative 4. Minus 2 times negative 1 is 2. Okay. We can simplify this. So how about I move the 2 to the other side and write negative 10 is negative b plus 2b is b minus 2c. Whereas the second equation is going to be 5 equals negative b plus c. Okay, so we end up with this pair of 2 equations for 2 unknowns. Move to the left so that you can see them. So that tells us c is 5. All right, then if c is 5, we can come to this equation, say, and solve for b. Gosh, I'm just gonna work to the left. Okay, so let's see, I'll just do it in a little box here. Okay, b is negative 10 plus 2c. But that's negative 10 plus 10, which is 0. So actually, there is not going to be a term of the form something over x minus 1, but we had to solve this out to see that. And then a is 2 minus 0 because it's 2 minus b, so 2. Okay, so our partial fraction decomposition is going to be 2 over x minus 2, nothing, or 0 over x minus 1, and then 5 over x minus 1 squared. And now we're ready to compute the antiderivative of our starting rational function. So what we have here is we just need to integrate 2 over x minus 2 plus 5 over x minus 1 squared. This is ready to go. I'm just going to rewrite this one time so that you can see the second term a slightly different way if you don't immediately recognize how to antidifferentiate that. So this is the integral of 2 over x minus 2 plus 5 times x minus 1 to the negative 2. Sorry, negative 1 is going to be in the antiderivative. So this is just a power rule. Term by term, we'll have 2 times natural log of the absolute value of x minus 2. This has an antiderivative of x minus 1 to the negative 1. So if I differentiated that, the negative 1 would come down, or rather I'm building up the antiderivative. The negative 1 would come down, so I need to cancel that out by having a negative there. Okay, all that to say that the antiderivative of this is negative 5 times x minus 1 to the negative 1, and then plus a constant of integration. And if you'd like to make this look more like what we started with in our integrand, this is natural log of, actually, you know what, let's do a little bit more. I'm just going to take this first expression and rewrite this as natural log of x minus 2 squared, like that, and then minus 5 over x minus 1 in a denominator, and then plus our constant of integration. Ultimately, we are going to want to integrate x to the fifth minus 2x to the 4 plus x cubed minus 2x squared plus x minus 1 over x cubed minus 2x squared plus x minus 2. But before we do that, we have to take this rational function and write it in a way which is much easier to work with. Since the numerator is a degree 5 polynomial, but the denominator is only degree 3, the first thing we have to do is rewrite this rational function so that any remaining rational functions have the property that the numerator's degree is less than the denominator's degree. So to do that, we'll do long division. I'm going to take the numerator and literally divide it by the denominator. It's not going to go in perfectly. We'll be left with the remainder, but that's going to give us the form of the rewrite that we would like to see. Okay, so we need to take x cubed and divide it into x to the fifth. So to get x cubed times something is x to the fifth, that something has to be x squared. Then we'll multiply everything here by x squared. So that's going to say x to the fifth minus 2x to the fourth plus x cubed minus 2x squared. Actually, a lot of stuff is going to cancel right now. Okay, everything cancels. I don't know if that's a little bit disappointing or what, but subtract the second line from the first one and we get 0. Bring this down, plus x minus 1. But now this power is less than this one, which means that we can take this rational function now and write it in the correct form. Our original, so I'm just going to write n over d to mean original numerator, original denominator. It's actually just x squared plus this over that. So plus the remainder, x minus 1 over x cubed minus 2x squared plus x minus 2. Okay, so take a look at that. Now we need to take this piece and break it apart using partial fraction decomposition. This particular cubic polynomial has the nice property that if you pull out the GCD from the first two terms, that would be x squared times x minus 2. And then the second two terms is just x minus 2, which means that this denominator factors into x squared plus 1 times x minus 2, like that. Okay, so let's just do the partial fraction decomposition here. To have equality, I will rewrite the x squared, but then we can ignore that in a minute. Take this expression now and break it apart. We have just a nice first order term. Let me write that first as, how about unknown numerator a over x minus 2. And then this is an irreducible quadratic. So if I write that in the denominator, I know that I need to have a numerator that's 1 degree lower. So bx plus c. Now let's just pair up this expression and this expression. Okay, I'm going to do the partial fraction decomposition here. So our numerator on the left is x minus 1. And then if I look at these two terms, what numerator would I get if I added these two fractions together using a common denominator approach? I would have ax squared plus a plus bx squared minus 2bx plus cx minus 2c. Again, we're going to have three equations for three unknowns. Let me go back to the left just to make sure that we have enough room to finish this computation. If I look at the degree 2 terms, actually, let's start with the constants. That's what I've been doing. So how about constants? Here it's negative 1. Here it is a minus 2c. Okay. What about degree 1? Here it's 1x, so 1 on the left. Here it is negative 2b plus c. And then on the left, we have 0x squared. So this is like 0x squared. So for a quadratic equation, it's going to be 0 on the left, and then a plus b on the right. That tells me a equals negative b. What I will do is replace negative b with a. So let's kind of try to organize this a bit. I have like the bottom half of the board. Okay. The first equation, I'm not going to change anything. So how about negative 1 equals a minus 2c? And then 1 equals, where I have negative b, I'm going to replace it with a. So this first term becomes 2a plus c. Let's now subtract off 2 copies of the first line from the second. So actually, I'm going to take this first line and multiply it by negative 2. So this one times negative 2. Oh, it looks like x minus 2. Sorry. Trying to think how to write this so that it's clear what I'm doing, and instead I've made it really unclear. Times negative 2. Okay, so that's going to be 2 equals negative 2a plus 4c. I'm going to add these two together, but let me also just stop for a second and let you catch up in case what I just did was a little bit hard to follow. Okay, picking up where we left off. If I add these two together now, I get 3 on the left. Negative 2a cancels with 2a, and 5c is the only thing left on the right, which tells me that c is 3/5. I can come back to this first equation the way it was written to immediately solve for a in terms of c. So we can say a is negative 1 plus 2c. So in this case, that's going to be negative 5/5 plus 6/5, which is 1/5. Okay, so that's the numerator a. And then b is just the negative of that. So immediately I also know b, it's negative 1/5. Okay, so now we've found the 3 missing coefficients a, b, and c. Just to drop them here before we move on to actually integrating this. A is going to be 1/5. B is going to be negative 1/5. And c is 3/5. Okay, so we have those as our numerators for our partial fraction decomposition. Let's finish this example by integrating it. Now let's integrate. The first two are ready. The third piece I will do in more steps. So we can go ahead and say that the antiderivative of the rational function that we started with is going to be x cubed over 3 plus 1/5 times natural log of the absolute value of x minus 2. Then I'll pull the negative 1/5 in front and write 1/5 times the indefinite integral of x over x squared plus 1 dx. And then similarly, I'll pull that 3/5 in front and write plus 3/5 times the indefinite integral of 1 over x squared plus 1 dx. Take a minute and finish this. So this one, you should know how to do it. This one, hopefully you recognize. I'll come back in a minute and finish this computation. Okay, let's see what you got. This is arctan. This is going to be a u substitution where I'll let u be the entire denominator, x squared plus 1, so that du is 2x dx. You can divide both sides by 2. All right, so then finishing up this example, we can say that the antiderivative is going to be x cubed over 3 plus 1/5 times natural log of the absolute value of x minus 2 minus 1/5 times the antiderivative of 1 over u du. Actually, no, that's not right. I have that 1/2 as well. And then this is going to be plus 3/5 arctan of x, then plus a constant of integration. Rather than rewrite the whole thing, let me just finish up this piece right beneath it. So this piece right here will turn into negative 1 over 10, natural log of the absolute value of u, but the absolute value of u is just the absolute value of x squared plus 1. That's always positive, so you don't need the absolute values, but I'll just leave them. Now let's take a look at this example where we want to summarize the guidelines that we've looked at for partial fraction decomposition. So imagine we had some large rational function whose denominator and factored form look like this. I don't have a numerator here, so we're not actually going to do the partial fraction decomposition where we solve for the numerators. Rather, let's just write down what it would look like. So we'll go left to right, term by term, to write down the smaller pieces that we would see in the decomposition with this denominator. So for this first one, we just have plain old x. So we would have a term that looked like a over x. Then for the second one, we have x minus 3. So similarly, we would have b over x minus 3. Now for this third term, we have x plus 1 squared. Because of the repeated factor, we would have c over x plus 1. So that's like degree 1, plus d over x plus 1 squared. So those are the two possibilities you would have with that repeated factor. Then for the next one, we have an irreducible quadratic x squared plus 5. So we would need a degree 1 polynomial in the numerator, like that. Then we have an irreducible quadratic squared. So we'd pick up 2 more terms for that that look like gx plus h over x squared plus 1 plus capital Ix plus j over x squared plus 1 squared. Without a numerator, that's as far as we can take this, probably for the better. But with that denominator, this would be the form of your partial fraction decomposition.